Yeah, hello everyone. I'm sure you can hear me. Okay, right. My name is Arin Akutekwe. I work as a data scientist with Fujitsu, and it's really a pleasure to do this presentation today. Good evening from United Kingdom. Good afternoon from other places, or good morning from where you might be joining us this evening. So today I'll be presenting on artificial intelligence in this bright talk, artificial intelligence methods, applications, and impact. And hopefully I would be able to also convince some of you to join the wonderful field of AI and data science. So I had to structured my presentation slightly different from what I planned out before when I was told that there were about 400 people or so that signed up. So I was, of course, guessing that everyone may not be very familiar with data science or AI and etc. So instead of perhaps putting in codes and some mathematical equations and functions, I have really changed it to really fit everyone. But all the links to like codes and other useful resources I've also included, not just in the presentation, but also as links and attachments here. Okay, we have just about 45 minutes, and so let's get to it. So artificial intelligence. So we're going to just look at brief origin and definitions. That's really a very broad field. I didn't really know which area to focus on that would, make everyone understand where I was driving at immediately. So I'm going to be drilling down all the way from AI down to convolutional neural networks, transfer learning, and also we'll look at the impact of artificial intelligence. So we'll look at these things that I've outlined here, a bit of introduction, machine learning, artificial neural networks, which some of you may have heard of before, deep neural network, deep learning, the buzzword of today, and CNNs, transfer learning, impact, levels of intelligence, and we look at question and answers. Okay. Right. So where did it all start? Some of you may know, some may not know, but this phrase was actually coined up by James McCarthy back in 1956 when he decided to kind of engage in call people together to figure out what what to do in terms of machines that can think, machines that can, because it was coming out at the time of development of lots of mathematical and statistical things, and so he proposed this 2-month, 10-month study of artificial intelligence back in Dartmouth College in Hanover, New Hampshire, back in 1956, and that's actually how the name AI came about. And there has been several other definitions. So I picked up these from the popular book by Stuart Russell, Artificial Intelligence: A Modern Approach. And there are different sides to it. So we can look at it from thinking humanly, thinking rationally, and many scientists have looked at it in various ways. Hugeland in 1985 looked at it as the exciting new effort to make computers think, machines with minds in the full and literal sense of it. And Cherniak and McDermott looked at it back in 1985 as the study of mental faculties through the use of computational models. And also other scientists and researchers looked at it in various ways as well. They have created machines that perform functions that require human intelligence, and in a rational sense, Pula et al. Looked at it as computational intelligence, as the study of the design of intelligent agents. And that word agent there connotes a lot, something that can move, something that has some sort of autonomy within itself. And we're going to be looking at it more. And so, but interestingly, any computer scientist really would have heard of Alan Turing. He came up with what I call operational definition back in 1950, as he called it as after posing some written questions that the system should be able to tell, you know, kind of which one, if a human interrogator will not be able to tell whether the response given to a system came from a human or from a computer, then that thing would really fit the definition of artificial intelligence. And so this is called the Turing test, and this test gave rise to the broad field of artificial intelligence. And it's interesting really to know that since 1950, this really has still remained valid. These areas that Alan Turing looked at back in the days are still valid. So I looked at natural language processing, knowledge representation, computer vision, automated reasoning, machine learning, and robotics. And you can find more of these in the book that I referenced, Artificial Intelligence, a Modern Approach. And so, and really when you look at the AI of today, it really still encompasses all these areas that Alan Turing looked at back in the 1950s. If you look at natural language processing, he said that to communicate successfully, the system should be able to at least be understood and communicate successfully, for instance, in a language such as English, okay, or Chinese or Japanese or some other kind of language. It has to be able to store and remember what it knows or what it hears, okay, and that's about knowledge representation. It also has to be able to answer questions and draw conclusions using stored information. And if you look at it right now, the knowledge representation part is like training a system or a robot or a machine, and it knows something, it remembers something, and then in automated reasoning, it's able to like predict using those stored answer questions and draw conclusions using those stored information. And this was, you can imagine back in the 1950s, for someone to come up with all these thoughts. The system should be able to also detect patterns and extrapolate information, adapt them to new circumstances. And that's what we call machine learning today, which is a subset of artificial intelligence. It also needs to perceive objects. It also needs to be able to see. And that's the computer vision part that we know of today. And the agent or robot or machine needs to also be able to move about and be able to manipulate objects. You know, it needs to be physically sort of active as well. And so all these put together sort of then gave rise to the definitions that we hear of today. For instance, if you go to a dictionary, you will see various definitions, and all these definitions are sort of efforts to put together indeed what Turing back in the 1950s managed to compress all together. And so you see the dictionary definitions like the Oxford Dictionary, theory and development of computer systems, be able to perform tasks normally requiring human intelligence. And you see many other sorts of definitions. But I will also want to add that, it's always a branch of computer science. So, if you are in the field or so, or looking to join the field, always mention it as a branch of computer science, dealing with simulation of intelligent behaviors. You can define it in your own way, but it's always a branch of computer science, and it might also be seen as a branch of computer science that deals with the design of systems with the abilities of exhibiting some kind of intelligence. In my own words, it has to be able to exhibit some sort of intelligence. And so, many other people have looked at AI in very different ways. If you don't know of Andrew, you probably are not obviously in the field, but Andrew is the chief scientist at Baidu and a professor at Stanford, and so he recently coined in this word that AI is the new electricity, and this is just recently, back in January or February of this year, because it literally now affects everything that we do. It's literally in everything, and I really encourage us to have a look at his talk. There's a YouTube link that I've put in the slides, which you would get after this presentation, or probably some of you have already gotten. He was just trying to point out that it's in everything. Okay, so search engines every day, recommender systems, self-driving cars, cell phones, everything really. Factories and data centers, loan approval systems, just about everything. And there is almost no field that would not be affected by this huge growth and interest in artificial intelligence. There is just about no field. And in that talk, really, he was given a kind of example that he cannot figure out how a machine will replace his barber that cuts his hair. And somebody actually said that he was going to design a robot that could replace his barber. Okay. So the field of artificial intelligence gave rise to the subfield of machine learning as we know it today. Again, most of you would be very familiar with the term machine learning and what it does. So most of the machine learning that we really see today is the supervised learning, okay, where, as I've put in this diagram, you show a computer something, like in this case, pictures of cats, and then you train it with algorithms, and then the computer system knows that this is a cat, and then when it sees a different image or picture, it's able to tell that yes, this is a cat with some very, very high accuracy, as we've seen various systems are able to do that today. So again, there are various links that I've left at different sections of this presentation that you can also have a look to see more about these methods. There are just so many of them, so many methods in machine learning. So just a very quick run through of the kinds of machine learning that we have currently. Supervised learning, just like the example that you saw earlier, you present a machine with examples of inputs and desired outputs, or labels as we call them. This is called training data, and then you go. The goal is to map that input to the outputs, so that when you bring fresh data or unseen data, the system will be able to know or tell that, hey, this is a cat or this is a dog or something like that. Classification and regression tasks are the examples. Unsupervised learning is, just as it sounds, unsupervised. So no labels this time. Nothing is given to the system, so the system is really left to discover hidden patterns or clusters in a group. And you see this a lot, as for instance, algorithms like k-nearest neighbors and PCA, etc., can be used for market segmentation. To literally just group things together. If you throw in a bunch of data, you don't know what the groups they are, these algorithms are able to tell you apart what kind of groups they belong to. And the final one, picking up great interest, is reinforcement learning, where this is found in your self-driving cars. For instance, the machine tries to find suitable actions to take in order to maximize rewards, and there are many different algorithms for that as well, Q learning, etc. And so the machine learning, or rather the data, has become sort of the new gold, really, because these systems or these algorithms are just as good as the data that you feed them. So, for instance, in the case of the supervised learning, if, for instance, the images that you feed into the system are not good enough, it will not be able to tell that the test image is a cat, for instance. And so, and also the advent of IoT. So we have now sensors in everywhere. We're looking at this kind of things at work in Fujitsu, installing sensors to be able to collect a huge amount of data and be able to, predict when a system will fail, and all this kind of things. These are driven really by big data. Again, a term that you would have heard of. We have enough data, incidentally. Okay, we're able to even scrape websites, literally. You can scrape images or text information from various websites and use them to develop or design your system. So, but how do we accomplish some of these? So, as mentioned, these are accomplished using machine learning models. Okay, so these models are simply algorithms, sequence of mathematical steps that the computer uses to learn. And there are, as mentioned, several of them, hundreds, perhaps even thousands, of all these algorithms in use today. So, so we are kind of drilling down, okay, because this 1 hour, actually, it's not even up to 1 hour. It's just under 45 minutes. It's not enough to really drill down into anything really, but I'll try my best to, as said, drill down to something that we can actually see some examples of in practice, and then yeah, okay. So supervised. Hello. Did someone ask? Did someone say something? Okay, I think I heard. Okay, sorry about that. So supervised learning examples, as we've mentioned, there are many algorithms, artificial neural network being the one that we will look at today. There are also support vector machines, random forest, generalized linear models, naive bias. These things enable us to perform classification and regression tasks. Unsupervised learning, as mentioned, K-means clustering, principal component analysis, hierarchical clustering, and also reinforcement learning. You have algorithms like Q-learning, SARSA, etc. And the references at the end, you will see links to these. So this is where we are at the moment. We've drilled down all the way to artificial intelligence, from computer science, artificial intelligence, machine learning, and we're now in artificial neural networks. And so let's keep drilling down and see how far we can go. So what are artificial neural networks? Some of you may know, and some may not know, but again, I'm assuming, of course, very wide audience, unlike the MSc class I had to teach on artificial intelligence at the university, or other students. So these are just algorithms that try to mimic the human brain. Okay, back in the 80s, they were really very, very popular and widely used. All of a sudden, they began to go away. Why? Because, well, there wasn't really much commercial value to them at that time. They took a lot of time to train, lots of mistakes and so on. It was really like a research thing, just a research thing. And but all of a sudden, it bounced back. As we know it today, deep learning has become the boss thing. So, and it's found in state-of-the-art applications today, as you would have noticed, lots of applications making use of deep learning methods, which we're going to also look at. And another reason, of course, faster and cheaper computers. So everybody can now afford a laptop, and these laptops have GPUs that also enable processing. You can also buy more advanced GPUs. Things have become a little bit cheaper than they were 10, 15 years ago. Also, availability of trading data. As I mentioned, data is now everywhere. Data is coming. The big data of today has made these things possible. So it's really driven by big data and then huge research interest currently. So lots of applications are being developed. Lots of people being involved, doing PhDs, etc. in this field. And so let's just look at ANNs just in a very brief sort of summary. As you know, neural networks try to mimic the human brain, and this is pretty much what goes on in our brain. Some 10 billion neurons in the brain. I put a reference in there as well. So when the signal from a neuron exceeds a certain threshold, it fires, and then the synapse is the point at which nervous impulse passes from one neuron to the other. And these neural networks simply make use of these neurons. They are just inspired by these methods, these brain systems. So that's pretty much what, that's almost like what goes on. But this a neural network is just a very, 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 very simplified version of what goes on, of course, in our brain. So as you can see, again, most of you would have seen something like this before. This is a very simplified neural network. It has, in this case, 1, 2, 3, 4, 5 inputs, and then it has a hidden layer that performs some computations, and then it has an output layer. And these normally go through some sort of activation function, like we would see. So this is a very simple example. And how do they learn? So it turns out that much of the real world data today are not linear. So I believe most of us are, of course, familiar with linear models, linear regression, etc., and many other forms of linear systems, generalized linear systems, the lasso, and many others. But then most real-world data, for instance, images are really not linear, and some other data out there cannot really be used in sort of with linear systems. So that's what these algorithms try to do. So how do they learn? I put out some steps here. So each neuron simply computes a mere combination of its inputs. It adds a bias term and passes the results through an activation function. So basically, the bias node is what allows the adjustment of this activation function. And I'll show us some of the commonly used activation functions in neural networks today. So learning is really adjusting the sensitivity of every neuron. So there are many parameters in the neural network, as you can imagine, adjusting the weights and the bias and the learning rate and so many things that have to be adjusted. The strength of each connection is called the weight. That's what the term used to represent the strength of the connections. And learns really by accumulating all these things learned from each neuron down to each neuron. And the network can then contain one or more hidden layers which contain all these neurons to compute various things. The output of the hidden layer can be thought of as a new representation of the data. And then the final output is, of course, the target variable. So for instance, if it's in a classification system, it's able to tell apart one class of maybe a binary, maybe something is a dog versus a cat, that kind of thing. And so when we have different layers at this hidden layer. We can call them multi-layer. Okay, so in this case, a popular type of ANN is the multi-layer perceptron. And perceptrons are simply a classifier. So, excuse me, sorry. I put in a link there if you want to know more about perceptrons and classifications and so on. Multi-layer perceptrons are simply ANNs where each node in each layer is a linear combination of all the inputs of the previous one. So, just really forward pass and forward propagation. So it turns out that how do we then make these things to learn? Okay, how do we train, as we call them in neural networks and machine learning? How can we fit the model to the data? So you need to basically, in neural networks, you need to find the weight and bias parameters that minimize a certain loss function. In deep learning, most time you will find the cross entropy used as the loss function, but simply loss functions are just a measure of how bad the system performs. So, and this idea is really from high school math. So if you remember gradients and slope, so that's really all. Find gradients of this loss function with respect to all the parameters of this model, all the weights and biases and etc. of this neural network. That's actually how the system is going to learn. So, to find the gradients, again, from high school math, depending on when you did it, but some in university, some in high school did something called differentiation, if you remember. So chain rule of differentiation can be used to accomplish this. So the calculations show that the gradients with respect to the parameters in a layer only depends on the error from the layer above it and the output of the layer below it. So, it becomes quite easy to learn or train in neural networks. And so the gradient for each layer can then be computed, in an iterative way, in a kind of a loop, such that, we can start from after the forward pass. You remember we talked about forward pass in multi-layer perceptron. So after the forward pass, we can start from the last layer again to use that error to propagate. We call it propagation, literally just to try to minimize that error again back into the network and go through several times, or we'll call epochs, until we get a very, very, very low error. So this process is called back propagation. Okay, it's not too difficult to understand, but again, there's a link there for you to see all the mathematical functions behind it and all the differentiations, etc. So I'm just trying to keep it simple for our courses today. And so what is then this deep learning or deep neural network that we've been hearing about? So from neural networks, we get this idea of deep learning, and they are just neural networks with several hidden layers. There's nothing more to read for those of us that may not know. It's just as we can see. So if you turn the image sort of in an upside down position, you can see the sense of depth, that something is going deep, 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 and with so many neurons. And so, for instance, images, really lend themselves very well to this sort of processing, because every image is like a 2D, it has a 2D nature. So a grayscale image, for instance, has this 28 by 28 dimension. A very popular tutorial on using deep learning to learn images is from this MNIST Dataset, Modified National Institute of Standards and Technology database. So it contains some 60,000 handwritten examples and 10,000 test examples, 10 classes, of course, digits 0 to 9. And the objective really is to learn a function that predicts digits giving an image. So if you write 9, or for instance, the system should be able to tell that you wrote 9, or that if it sees 9, it should be able to tell apart that that this is 9 versus this is 8, and then measure the accuracy on the test set. So this was really championed by Jon LeCun, and I've put a link there to his website, and you can read more about this. He really championed this aspect of research, and this is how, of course, the data set look like. So I've just done this plot in Python, and you can also do this yourself. So there's a link there. You can try some of this yourself using not just TensorFlow, but also perhaps other libraries. So I've seen presentations where people are really writing code, and the audience, of course, they don't have the same environment, so they are kind of lost. So, but I've put examples where you too can find this and just see how it works. Practice yourself, and it's really not that hard. So the dataset looks like this, and there are the system learns quite very well, like up to 98% accuracy. So in this case, the example there, 3 layers in the neural network, an activation function using, I think I missed the slide on activation function. I think I did. Oh, there it is. Sorry about that. So these are the activation functions that we have in neural networks. I think I double-clicked or so. So basically, the sigmoid activation function, the hyperbolic tangent, and the rectified linear unit. So you would probably come across these as you perform some of these tasks yourself in the links that I gave. So because I really want us to, at the end, play with these things and see how they work. So these are the activation functions that we have in neural networks. And so if I go back to where I was, so the system was able to achieve quite a high accuracy of some 98.12%. So that is 188 errors in 10,000 test examples, which is quite good. Now the sigmoid, so that's okay, I'll still come to that, but you can try the various activation functions. So for instance, the sigmoid here gave an accuracy of 95%, but the rectified linear unit gave up to 98%. So of course, a good GPU today would be faster. NVIDIA GPUs or some kind of good GPU would be much better to compute these things with, because of course they lend themselves to arrays. Okay, one question. The question, sorry. Difference between computer vision and supervised learning for image recognition. Okay, let me just answer the question quickly. Supervised learning is inside, so the question is, can you explain the difference between computer vision and supervised learning? So, for instance, the example that we'll still come to, and some of the examples that you see online, is still supervised learning. So, we're trying to classify images, okay? So, this is, well, we do some of these with OpenCV for computer vision. Okay, so supervised learning is teaching a system, providing data, and teaching a system how to learn. Okay, so if it's going to tell apart that something is a cat, for instance, you must have provided images of cats, for instance. Okay, I hope that answers the question. Right. So We've seen the example of multi-layer perceptrons in hand digit recognition. So, but there's a problem. So, when if you shuffle the data, okay, so these are 7210411 and so forth. If you shuffle this data and train again, now the classification accuracy is not really affected. But however, the result that you will see when you print out the image, like I printed out, like for instance, assuming you've done this and you've done this plot function, for instance, you won't find something useful again. It will look like just white and black, dots or rashes or something like that. So what's going on here? It's because of the nature of these algorithms. They don't really know about how close each other digit or each other pixel is really, so they don't take that into account. So this is how convolutional neural networks came into play. And okay, so this is where we are right now. We've moved from ANN to deep learning to convolutional neural networks. And so what they try to do really is to match parts of an image rather than the whole thing. So in the previous example that we saw, you put in a whole image, for instance, of a cat or a dog or something, and then you use this very big metrics to do your multiplications. But instead of computing one big matrix, for instance, of the whole image, the idea here is just to perform lots of little matrix multiplications against each tiny patch of the image and store its local activation. Okay, so performing these convolution using two functions to produce a third function, so it's really an idea from mathematics, and it really works so well. So they also share parameters across the convolution kernels, and we'll see a very good example here by Brandon Roher from Microsoft Research. I encourage you to have a look at that link. He really explained this quite well. So each feature, for instance, in this image here, so each feature can be seen as a mini image or 2D array. So for a new image, then the convolutional neural network tries every part of the image to match the feature. So we've taken out this small green portion, taken out this small red portion, taken out this small pink portion, and then for a new image, we want to see how the little patches match in the new image than trying to match the whole thing. And that's the idea behind convolutional neural networks. So they contain several convolution layers. So each of these is called a convolution layer. And then the pooling layer tries to reduce the amount of data that needs to be processed. So, and it's just a way of, trying to take a large image and shrink them down while preserving the most information. So when we then map, when the algorithm tries to map these little images, it produces a filtered version of the image, and then the local activations, depending on how you initialize the weight, local activations are stored, and then we try to pick out the most important information, which is represented by the maximum value in that filter. So the filter is the layer and the small layers of local activations. And in CNN or in deep learning technology, it's called max pooling. So you're just basically trying to take the highest value represented by each of the filters. So you can see this example here in the link that I've given there, and of course in the example by Brandon in the other link there. So I encourage you to look at these things. And Jon LeCun also, of course, pioneered this research back in 1998 and used the CNNs on the MNIST Dataset that I mentioned before, and gave an accuracy of over 99% accuracy, and that is 78 errors in 10,000 data sets. So that is very good, and that is how today we use CNNs to make machines to see, apparently. So it's able to see and recognize that something is this and tell it apart from that. So, and it's really, it turned out to be really quite advantageous, less parameters to learn due to small local kernels instead of one big chunk, shared parameters, faster to train because, the weights are shared and the gradients, average for every location. So it turns out to really be quite good. And again, this example tries to depict that. So one convolution layer, the rectified linear units are used to as activation functions, mostly in CNNs, to turn something that is 0 to 1. Basically, that's what the Redo does. It turns something that is 0 to 1 in order to make the final activation better. So again, this example was from Brandon. I encourage you to have a look. But in the end, we use CNNs to come to this kind of thing where it sees the image of a car, and then this image goes through all these layers, and then the system is able to recognize indeed that it's a car rather than a truck or an airplane or a ship or a horse when in the test set. So this has really been quite very, very powerful in today's deep learning technology, and this pioneering work by Andrew and other researchers. Also, this is not just able to tell that it's a car, but it also can tell you that it's exactly Audi A7 because of the classification as well that goes on at the top of the layer. So you can see the various filters that this is how the system is able to really see by looking at the small patches and trying to map which patch or which little portion matches the new image. We're almost running out of time. So how do we make them better in practice? So because I mentioned too many parameters, it turns out that there's no best way. Okay, you change. You have to, depending on your data set, you have to change various things, the hidden layer and all that to make your system better the way it should be. So that also poses another problem. Okay, so the problem is, of course, that few people are able to train this entire data set. I don't know, millions of images that you have to train, for instance, for your own particular problem. You probably don't have that time, or maybe even the resources to do that. So you may not have all the data as well for your own particular case. So this problem can be solved through what we call transfer learning. So we've gone from deep learning to CNNs, and we are now deep here into transfer learning because it makes use of both excuse me, it makes use of both supervised and unsupervised learning methods. And so the whole idea is to transfer a learned representation from a related task. So if you have a related task in ImageNet, for instance, you can transfer it to another task that is also related to images and try to learn from there. So for instance, you can use a pre-trained network on a different domain for a different source task and adapt it to your own use case on your own target task. And there are various scenarios that today. So for instance, using CNNs as a fixed feature extractor. So you can chop off the last fully connected layer of that CNN pre-trained, for instance, on ImageNet, and then treat it treat the rest of the CNN as a fixed feature extractor for your new data set. again, I put examples or links to where we can find more information on that. So once the features have been extracted, you can then use a softmax classifier on SVM to classify the final as a classification layer for the final for the top layer, as we can see from here. So this top layer is now, for instance, an SVM, and you can tell apart whether something is a car or the A7 or A8 or something like that. Okay. So there are, and it does perform well in practice. So this paper here, and of course many other papers, show that they do really perform well in practice. So this was the result on Oxford datasets, 102 flower datasets, and this research here, the algorithm CNN with SVM was found to be better than some other previous algorithm. So if you look at this paper, you also find more information, but they do perform well in practice because you have very little training and you have better results in most cases. So there are also other scenarios. The top layer can also not just be replaced, but also the weights can also be fine-tuned using backpropagation. And also the final scenario here, I gave a link here. So basically, Cafe and many other projects out there, the people release the final CNN parameters and checkpoints, etc. And this can be used for fine-tuning. So you can, for instance, go here, assuming you are trying to build an application and get things from trained models. And there are also other domain applications, unsupervised domain application from this link, unsupervised domain adaptation as well. So I've also provided a link to deep learning libraries that are used in practice. I personally use TensorFlow and some Theano as well, but there are also very many others. So how does this impact everybody? Okay, this is something I've also found myself engaged in terms of discussion and conversation, but it depends on how you want to look at it in terms of whether from a pessimistic view or from an optimistic view. But studies show that these growth in AI have also just created more jobs. So those that are thinking about job losses, for instance, it has actually led to more jobs being created. And this research by Accenture just last year that AI has the potential to double the annual economic growth rates of all these countries that are studied. So I put a link here as well. So it is something good. It's something I encourage us to come into. We're just able to, my time is just up. We're just able to touch a few, but we are still at this artificial narrow intelligence. We're not yet at artificial general intelligence, where machines become good in most fields than humans, and we are far, far, far away from artificial super intelligence, where the machine has become smarter than everybody in every field. So we're not yet close to this. So some expressing concerns that